In this video, we will discuss about the structure of the DNA right from the formation of its monomeric unit called nucleotide, and from nucleotide to the formation of the polynucleotide. What are the components of the nucleotide, how it is formed, and from here how the what we call the polynucleotide is formed, what are the bonds being involved, we will see. Now coming to the nucleotide, these nucleic acids, that may be DNA or RNA, they are composed with a monomeric units called as a nucleotide. Coming to the what we call the components of the nucleotide, consider this one as the monomeric unit of the nucleic acid, that is a nucleotide, and this nucleotide composed by the three major components. They are nitrogenous bases and the pentose sugar, and third one is the phosphate. Coming to the nitrogenous bases, then two types of the nitrogenous bases are present. They are purines as well as the pyrimidines. Adenine as well as guanine, they comes under the purines, while the cytosine, uracil and thymine, these comes under the pyrimidines. And coming to the second important component, that is pentose sugar. Two kinds of the pentose sugars we observe. Ribose is the pentose sugar in RNA and deoxyribose is the pentose sugar in the DNA. And the third important component is the phosphate group, and which contributes negative charge to the overall nucleotide, to the polynucleotide, that may be DNA or RNA. Usually they are with the negative charge because of this phosphate group. Then coming to the nitrogenous bases. Then what are these nitrogenous bases? Now let us see. These nitrogenous bases are the heterocyclic organic compounds containing nitrogen and carbon in their ring structure. And these are acting as the fundamental building blocks in the case of the nucleic acid. They are DNA as well as RNA. These are the heterocyclic organic compounds. Then come to the heterocyclic organic compounds. Heterocyclic organic compound, it's a type of the organic compound that contains at least one ring structure, and that is made up of atoms at least two different kinds of the elements. Typically carbon in combination of one or more other elements such as nitrogen, oxygen, sulfur or phosphorus. Nitrogenous bases are the heterocyclic compounds. Here we can see these are composed with the nitrogen. In other vertical locations, the carbon is located. So here this nitrogen bases, that may be the purine as well as the pyrimidine, both are the heterocyclic organic compounds which consisting of the nitrogen as well as carbon in their ring structure. Now let us come to purines as well as the pyrimidines. These nitrogenous bases broadly classified into two categories as we discussed earlier. They are purines as well as the pyrimidines based on the number of the rings present in their structure. In the case of pyrimidines, only one ring, while in the case of the vertical purines, two rings are present. So nitrogenous bases are broadly classified into purines as well as the pyrimidines based on the number of the rings present in their structure. Then coming to the purines. In the case of the purines, now let us say then what exactly the purines are. Purine is a heterocyclic aromatic organic compound that consisting of two rings, the pyrimidine as well as imidazole, they fuse together and form the two ring like structure. So here we can see, then this is the pyrimidine ring, and here we can see the imidazole ring. In the pyrimidine ring, we can see the presence of the 2 nitrogens as well as 4 carbons. Here one nitrogen and here one more nitrogen, and carbons we can count 1, 2, 3 and 4. And in the case of the imidazole ring, then here it consisting of the 2 nitrogens as we see here, and in the remaining places usually 3 carbons are present. So basically thus purines are composed with the 2 rings, they are pyrimidine ring as well as imidazole ring. Then coming to the bases that comes under the purines, they are adenine as well as the guanine. Then the basic difference here we can see at this head position amine, and in the case of guanine we can see the oxygen at the head position. Then coming to the numbering in the case of the pyrimidine, the basic things now let us see. In the case of the pyrimidine ring, it is with 2 nitrogens. Then we have to consider the nitrogen which is present at the top position is labeled as the N1. And we have to ensure that other nitrogen should get the least number. In that case, then this is the vertical the N1, and at the second position the carbon, third position again the nitrogen, and the fourth position the carbon, fifth position the carbon, and the sixth position again the carbon. Then from there, then we have to continue the numbering. Then this is the seventh position, eighth position carbon, and ninth position again the nitrogen. And in the case of some of the literature, we see that the imidazole is located towards the left side. In some other what we call the text, they mention, they show, they exhibit this imidazole ring towards the right side. Whatever maybe the orientation of the imidazole, we have to label number 1 position to the nitrogen which is located at the top position of the nitrogen. Here also we can see this is the numbering, and here in this case also, then we have to give the number 1 for the nitrogen present at the top position. So here in this is the way how we have to numbering, irrespective of the clockwise or anti-clockwise. We have to keep our focus on the facts that the nitrogen present at the top position must be labeled as the N1, and we have to ensure that other nitrogen should get the least number, irrespective of the clockwise or anti-clockwise. These are the things we have to consider. Then more precisely here we can observe these things. The imidazole ring color is changed here. Then here the ring is towards the left side here, and the vertical ring is here towards the right side. Irrespective of the orientation where this particular imidazole ring is, they are exhibiting, then we have to stick on to this, the numbering. The top nitrogen must be labeled as 1, and other nitrogen which is present at the basal position should get the least number in the case of the purines. Now coming to the pyrimidines, the second type of the nitrogenous bases which are composed with only 1 ring. Then coming to the chemistry related to the pyrimidine. Pyrimidine, it's an aromatic basic heterocyclic organic compound. In the case of the pyridine, usually it is composed with the 2 nitrogen as well as the 4 carbons. Now coming to the what we call coming to the numbering. In the case of the numbering, the tricky thing then we have to follow here. In the case of the pyrimidines, nitrogen which is located at the basal position here at the base is labeled as N1. In the case of the purines, nitrogen present at the top position is labeled as N1, but in the pyrimidines, nitrogen which is located at the basal position is labeled as the N1, and we have to ensure that other nitrogen should get the least number. So that is the reason Then we move in this order: nitrogen 1 and the carbon second position, and the third position the nitrogen, and the what you call the fourth carbon, fifth carbon, sixth carbon. Then here this is the what you call the same thing, irrespective of the orientation, whether that may be oriented towards the right side or left side. Then this is the same rule we have to adopt. If you look at the vertical list of the ring structure, the oxygen at the second position, that is oriented towards the right side. In the second one, it is oriented towards the left side. Irrespective of the way how they are exhibiting, then we have to assign, we have to label the first position to the nitrogen present at the basal position, and we have to ensure the least number for the other nitrogen present in the ring. Then coming to the types of the pyrimidines, by combining both DNA and RNA, we see the presence of the three different kinds of the pyrimidines. They are cytosine, uracil, as well as thymine. These are the three kinds of the nitrogenous bases that comes under the pyrimidines. Then coming to the tricks that work to remember the things in the easiest manner, now let us see. So usually here in the case of the nitrogenous bases, the purines as well as the pyrimidines are present. Sometimes we get confusion which kind of the nitrogenous bases comes under the purines and the pyrimidines. For that, then is simple trick, let us see. Consider there is a huge treasure within the Egypt pyramid. What we have to do to take it out? For that, we need to cut the pyramid. We need to cut the pyramid. Now let us see. Cut the pyramid. So here there is this the pyramid, then that is to represent the pyrimidines. Cut the pyramid. Cytosine, uracil, and thymine. So cut the pyramid, if you remember, then we can say that this 3 comes under the pyrimidine. So remaining 2 comes under the purines. And one more thing, then this is our WhatsApp language. Whenever we want to scold someone like a fool, usually we don't write the complete YOU, ARU, you are a fool, something like we don't write. Usually we write you and you are fool. Then what is this you are fool story here? Uracil is present in the case of the RNA. You are a fool. Uracil is present in the case of the RNA. So if uracil is present here, then the other is present in the case of the DNA. This is the simple way to remember the kind of the pyrimidine present in the case of the RNA as well as the DNA. So here as a summary, here we can say adenine as well as guanine comes under the purines, and the cytosine, uracil, and thymine that comes under the, while the cytosine, uracil, and thymine that comes under the pyrimidines, and uracil is specific to RNA, while the thymine is specific to the DNA. Then on summary, here we can conclude in this way. The adenine as well as guanine, these are the purines. They are present both in the case of the RNA as well as DNA. And the cytosine is the pyrimidine, which is common in the case of both RNA and DNA. And the uracil is especially present in the case of RNA. We don't see them in the DNA. And the pyrimidine, like the thymine, is especially present in the case of the DNA. Then coming to the sugars. And when we see what is the chemical nature of the sugar, it is a 5-carbon structure with furanose form. That is the beta furanose form. Then what is this furanose form? A furanose ring is a cyclic carbohydrate structure with 5 members consisting of the 4 carbon atoms as well as 1 oxygen atom. So here we can see that in the case of the furanose form, then this is the furanose ring. 1, 2, 3, 4 carbons are present and 1 oxygen is present. But as we discussed, this is a 5 carbon, the sugar. In these sugars, usually 4 carbons are present within the ring and 1 carbon, the 5th carbon is present outside the ring. Now coming to the types of the pentose sugars. Usually we see the presence of the two different kinds of the pentose sugars, ribose as well as deoxyribose. Ribose is the pentose sugar present in the RNA, while deoxyribose is the pentose sugar present in the case of the DNA. Then coming to the one of the important notation before that, if you observe both the rings, like in the case of the nucleoside or maybe in the nucleotide or maybe in the DNA or maybe in the RNA, then when you look at the vertical structural component of them, the nitrogenous base here, here we see the presence of the nitrogen as well as carbon here. Consider at the second position carbon is present. And in the same pentose sugar also carbons are present. Then at this second position also carbon is present. So we need to have the specific notation to differentiate the carbons present in the nitrogenous base with that of the carbons present in the case of the pentose sugar. For that, usually we use a specific notation called as the prime. Usually this prime is denoted by a superscript, then this is the prime symbol as the superscript. Then what is the main function of this introduction of this notation? Its main role is to differentiate the carbon positions in the pentose sugar and the carbon positions present in the nitrogenous bases in the nucleic acids. So by using these primes, now let us see the way how we can represent the carbons present in the furanose ring, that is what we call the pentose sugar. Carbon present here, the first prime carbon, and carbon present here, the second prime carbon, and this is the third prime carbon, and fourth prime carbon, and this is the fifth prime carbon. The same notation we use while representing the two poles of the DNA also. Later we will discuss about that. And coming to the two types of the sugars present in the case of the nucleic acid, they are the ribose sugar as well as the deoxyribose sugar and the deoxyribose sugar. Then what is the basic difference here? When you look at the second prime position, in the case of ribose, here we can see the presence of the OH group at the second prime position. In the case of the DNA, then look at the type of the sugar present here. At the second prime position, oxygen is absent. As oxygen is absent, this kind of the ribose, we call them as a deoxy. Oxygen is absent, deoxyribose. So the basic difference is the presence or absence of the oxygen at the second prime the position. In the ribose, OH is present, while in the case of deoxyribose, then only hydrogen is present here. And this ribose is the type of the sugar present in the RNA, and this deoxyribose is the type of the sugar present in the case of the DNA. Now coming to the phosphate. The third important component of the nucleotide is the phosphate, and usually then this is the simplest and most common, the phosphoric acid. Usually orthophosphoric acid is present, and its chemical formula is H3PO4, and usually it is a weak acid with 3 acidic hydrogens. In the normal condition, usually these hydrogens will be removed, deprotonated, and usually that gives the negative charge for the molecule. And overall, this phosphate component of the nucleotide is responsible for giving the negative charge. See, the 3 important components of the nucleic acids are the nitrogen bases, the pentose sugar, and orthophosphoric acid. Then coming to the type of the nitrogenous bases, in the case of the DNA, adenine and guanine are the purines, and cytosine and thymine are the pyrimidines present in the case of the DNA. Then coming to the RNA, nitrogen bases, type of the nitrogen bases present in the RNA. Adenine and guanine common. And next one, coming to pyrimidines in the RNA, cytosine and uracil. These are the pyrimidines present in the case of the RNA. So here, when you look at the particular type of the nitrogenous bases, all are common. In the case of DNA, thymine is present, and in the case of the RNA, uracil is present. Then the second component is the pentose sugar. Ribose is the pentose sugar present in the case of the RNA, and deoxyribose is the pentose sugar present in the case of the DNA. Other important component is orthophosphoric acid. This orthophosphoric acid is common both in the case of the DNA as well as RNA. Then coming to the types of the bonds that are being involved in the formation of the nucleotide as well as the formation of the polynucleotide. Now let us see what are the bonds present within the nucleotide. That means for the formation of the nucleotides, what are the bonds that they are being involved? They are glycosidic bond as well as phosphoester bond. Coming to the glycosidic bond, then this glycosidic bond, it's a covalent bond that formed between the pentose sugar as well as the nitrogenous base. Then this is the what we call the nitrogenous bases here, and this is the what we call the pentose sugar. Whatever the bond that is going to be formed in between the nitrogenous base and the pentose sugar, we call it as the glycosidic bond. And what are the components they are being involved in the formation of this bond? Now let us see. From the pentose sugar, the hydroxy which is present to the first prime carbon, that makes a bond with the nitrogenous bases. In the case of the what we call the purines, the hydrogen present at the 9th position, that is being involved in bond formation, while in the case of pyrimidines, the hydrogen which attached with the nitrogen 1, that is being involved in bond formation. Two ring structure, the purine. Then this is the what we call the hydrogen, like that is present at the this is the what we call the hydrogen, the nitrogen. And in the case of the pyrimidines, the hydrogen which is present to the what we call the first nitrogen, that is being involved in the glycosidic bond formation. During the formation of this bond, this hydrogen as well as the hydroxy from the pentose sugar, they are removed as a water molecule. Then that leads to formation of the glycosidic bond. Then here also in the case of pyrimidines, hydrogen linked to the nitrogen at the first position, and the OH group, the first prime hydroxy group, they removed as a water molecule, and that leads to the formation of the glycosidic bond. Then here we can say, then these are the glycosidic bonds with the purine, and next with the what is the pyrimidine. Then coming to the phosphoester bond, the second kind of the bond which is being involved in the formation of the nucleotide is the phosphoester bond. Now let us see then what is this phosphoester bond. This phosphoester bond is formed between generally ester bond is formed between the acid as well as the alcohol. In the case of the nucleic acid, the acid which is being involved in the formation of the phosphoester bond is the phosphoric acid. That is the reason we call it the phosphoester bond. Then OH from the phosphoric acid and hydrogen from the OH group of the pentose sugar, they are being involved here. They are removed as a water molecule. Then this is the what we call the phosphoric acid and the pentose sugar here. During the formation of the bond, OH from the phosphoric acid and hydrogen from the pentose sugar, they are removed as a water molecule. That leads to formation of the phosphoester bond. Then this is the phosphoester bond which is formed between the phosphoric acid and with that of the pentose sugar. When we see the overall structure of the monomer, that is called as a nucleotide, it is composed with the three components, the nitrogen base and the pentose sugar and the phosphate here. And we discuss about the type of the bonds present here. Between the nitrogenous base and the pentose sugar, glycosidic bond is present. And between the pentose sugar and the phosphate, the phosphoester bond is formed. These are the two types of the bonds, glycosidic bond and the phosphoester bond, are responsible for the formation of the nucleotide. This table is about the nomenclature of the nucleoside, nucleotide, and where they are present in the nucleic acids, like the DNA or RNA. Then coming to bonds present between the nucleotides, usually that is the phosphodiester bond. The name itself is suggesting the presence of the two ester bonds. Before that, now let us see one phosphoester bond already that is present between the 5' hydroxy of the pentose sugar with that of the phosphate. Then this is one nucleotide. Then here this is the nitrogenous base, pentose sugar, and its phosphate. This is one nucleotide. Now let us come to the second nucleotide, that is with the guanine, pentose sugar, and the phosphate. Now here already the existing phosphoester bond is present here. Now the new phosphoester bond is formed between the 3' hydroxy of one nucleotide, 3' hydroxy of the one nucleotide with that of the 5' phosphate of the other nucleotide. That is from the two different kinds of the nucleotides. Then here also, then hydrogen from the alcohol, OH from the phosphoric acid removed as water molecule, and new phosphoester bond is formed here. So here on conclusion, then we can say this 3' to 5' phosphoester bond is formed between the 3' hydroxyl group of one nucleotide and a 5' phosphate group of the other nucleotide. So two nucleotides are joined together by a two phosphoester bonds. So now let us see then how this bond is formed. Then here, then this we can say, then this is one phosphoester bond, the new bond, and already this is the existing bond while the formation of the nucleotide. So here these two phosphoester bonds are present here between the two nucleotides. The ester bond here, then here also phosphoester bond. So these two phosphoester bonds are linking the adjacent nucleotide. This is the nucleotide one, and this is the next nucleotide. So that is the reason, on conclusion we can say these nucleotides are joined together, adjacent nucleotides are joined together by two phosphoester bonds. Even the orientation also from the 3' to the what you call the 5' direction, we can say from the 3' to the 5' side we can see. Then this is the phosphodiester bond. Nucleotides, they meet to form the polynucleotide structure of DNA or RNA. And here, then this is the what you call the phosphoester bond one, and this is the phosphoester bond, that is the second phosphoester bond formed between these two. So here this is the way how the the number of the phosphoester bonds they are forming and joining the adjacent nucleotides together. Then when you look at this one here, the backbone, that means the structural framework of the DNA is formed by the alternating sugar and the phosphate molecule. Now if you see the overall structure here, there the phosphate is present here and the pentose sugar is present here. Then again the phosphate, then here this is again the sugar, then here again the phosphate and sugar. These nitrogen bases, they are projected inwards. So the backbone of the DNA is formed by the phosphate as well as the sugar. This backbone structure that provides stability to the DNA molecule, and it serves as the support for the nitrogenous bases which are attached to the sugars. So this backbone is giving the structural support for the nitrogenous bases which are attached to the sugar. Now here we can see the way how the backbone is formed here. The phosphate sugar, phosphate sugar, phosphate sugar, and the nitrogen bases are projected inwards. And when we see here the two ends of the polynucleotide, towards one side here we see the presence of the free phosphate. Towards which side it is present? Towards the 5' side. And coming to the other side, in the case of the other side, then what is present other side? Then the free OH group is present here, which is linked to the 3', the position of the carbon. So here these are the two terminals of the polynucleotide. One side free 5' phosphate is present, while the other side a free 3' hydroxy groups are present, and these two are the two poles of the DNA, and these two are the two terminals of the DNA. Towards one side free 5' phosphate, and towards the other side free 3' hydroxy groups are present. This is about the structure of the nucleotide as well as the polynucleotide from beginning.